Infinite series are things we studied in pre-calculus. An infinite series looks like this. Sigma A subscript K. The K subscript starts at 1 usually. The starting number does not have to be a 1. It could be 0 or 2 or 3. But the thing up here does have to be infinity, so we can call this an infinite series. And the meaning of this symbolism means A sub 1 plus A sub 2 plus A sub 3 plus dot 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 plus A sub n plus dot 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 forever. These terms, A sub 1, A sub 2, A sub 3, etc., are called the terms of the series. A sub n is called the nth term. Partial sums means the following. S subscript 1 is exactly the same as A subscript 1. S sub 1, A sub 1, same thing. They both mean whatever this first term is. But S sub 2 means the sum of the first two terms. It's called a partial sum because it's only the sum of the first two terms. S sub 3 means the sum of the first three terms. Period. If I say S sub n, I mean the sum of the first n terms. That's it. None after that. In other words, when I say S sub n, I mean sigma A sub k. The k starts at 1 and goes only to n. If the sequence of partial sums has a limit, we'll call the limit s. If it has a limit, we'll call the limit s. As n approaches infinity, the series converges to the sum s. If this were the case, we write the following. Sigma A sub k, where k starts at 1 and goes to infinity, meaning A sub 1 plus A sub 2 plus etc. plus A sub n plus etc. This infinite series is equal to s. Otherwise, we say the series diverges. We're going to look at a few examples. The main point of looking at the examples is to clarify all this vocabulary, like the word sequence, the phrase partial sums. The phrase partial sums has a limit as n approaches infinity. The vocabulary words converges and diverges. So when we do exercises, they should clear up all the vocabulary. Page 485, exercise 8. It says 2 minus 1 plus 1 minus 1 plus 1 minus 1 plus dot dot dot, continuing forever. So, this is an infinite series. Infinite because of the dot 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 at the end. Series is just numbers added together like this. These are the terms of the series. S subscript 1 means the first term. S subscript 2 means the sum of the first two terms, which you can see is 1. S subscript 3 means the sum of the first three terms. 2 minus 1 plus 1, which is 2. S sub 4 means the sum of the first four terms. 2 minus 1 plus 1 minus 1, which is 1. S sub 5 means the sum of the first 5, which is 2, etc. So when we say the sequence of partial sums, sequence of partial sums, we're talking about this list of numbers. 2, 1, 2, 1, 2, right here. This list of numbers is a sequence. It's called the sequence of partial sums. It is clear that the sequence of partial sums does not have a limit. As n approaches infinity. In other words, these numbers are not getting closer and closer to something. They're just going back and forth. 2, 1, 2, 1, 2, 1. When this happens, when the sequence of partial sums does not have a limit, we say the series diverges. And I would like to tell you the directions for this exercise now that we're done with it. The directions are: compute the limit of the partial sums to determine whether the series converges or diverges. Well, the sequence of partial sums does not have a limit. So the answer is the series diverges. That's answering the question. Let's look at exercise 10. It's 1 plus 0.5 plus 0.005 plus 0.0005 plus dot dot dot. S subscript 1 means exactly the same as A sub 1, which is this term. S sub 2 means the sum of the first two, which is 1.5. S sub 3 is the sum of the first three, which is 1 plus 0.5 plus 0.005. Actually left one out here, so let me fix this. Bringing up over here is okay. If you copied something wrong, it's 1 plus 0.5 plus 0.05 plus 0.005 plus 0.0005, etc. I think I left one of these out. This is S sub 1, this is S sub 2. S sub 3 means the sum of the first three. 1 plus 0.5 plus 0.05 is 1.55. The sum of the first four, S sub 4, means add the first four here. And we get 1.555. What we notice here is that this sequence of partial sums does have a limit. What I mean is these numbers here, 1.5, 1.55, 1.555, they're getting closer and closer and closer to 14/9. This is, when I say 14/9, I mean 1.5 repeating. And each of these numbers is getting closer and closer and closer to that. The sequence of partial sums in this list of numbers right here has a limit as n approaches infinity. N is the subscript, again gets larger and larger. Conclusion, the sequence of partial sums has a limit. The series converges. And that is the answer. Okay. Okay, so now we're going to talk specifically about geometric series. The geometric series looks like this: sigma a times r to the n minus 1, n starting at 1 and going to infinity. Or sometimes you'll see it like this: sigma a times r to the n, where n would start at 0 and go to infinity. Think about how these are exactly the same thing. If you make 1 the starting n value, this will be a times r to the 0. If you make 0 the starting n value, then this will be a times r to the 0 also. And all the terms will be the same. These are two different ways to write the same thing. If the exponent is n minus 1, the starting n is 1. If the exponent is just n, then the starting n is 0. And so either of these is a plus a times r to the first power plus a times r to the second plus a times r to the third plus, etc., a times r to the either n or n minus 1 plus, etc. And we need to learn or remember from pre-calculus, a geometric series, which looks like this, or this, or this, converges to the sum a over 1 minus r if the absolute value of r is less than 1. And diverges, that means you can't find the sum, diverges, if the absolute value of r is greater than or equal to 1. We're going to do 2 examples from page 485, starting with number 16. We have 3 minus 0.3 plus 0.03 minus 0.003 plus 0.0003 minus, the terms, notice, are alternating sign, positive, negative, positive, negative, positive, negative, dot, 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 3 times negative 0.1 to the n plus dot, dot, dot. This, which is, I'm just copying out of the book, could have been written like this: sigma 3 times negative 0.1 to the n, where the first n, which is the exponent, is 0. And the exponents go, the n goes from 0 to 1, 2, 3, and so on. Because when n is 0, all this becomes the first term. When n is 1, all of this becomes negative 0.3, and so on. So since this is geometric, because there's a common ratio, the common ratio is any one of these numbers over the one immediately before it. And it's not a coincidence that it's this number in the parentheses. Take any number, we could have taken that number over the one before it. Every time you do take a number over the one before it, you're going to get negative 0.1. Since the absolute value of r is less than 1, the series converges. This is r right here. If the absolute value of r is less than 1, the series converges to a over 1 minus r. That's the formula, a over 1 minus r. A means whatever the first number is. With all these numbers added, that's a. 1 minus negative 0.1. Because r is negative 0.1. A over 1 minus r. We simplify that. Multiply the numerator and denominator by 10 to simplify this to 30 over 10 plus 1. Minus minus becomes plus. Multiply each by 10. So 30 over 11. And we can summarize this whole problem by saying sigma 3 times negative 0.1 raised to the nth power, where the n is actually starting at 0, going forever. N is 0, then 1, then 2, then 3, and so on, is equal to 30 over 11. And I already wrote that the series converges. Down here I'm saying what it converges to. And we're going to just look at one more. Number 20. It says this: sigma 5 to the n over 6 to the n plus 1. And the n is starting at 0, going to infinity. So this is given. If n is 0, 5 to the 0 is 1, 0 plus 1 is 1, 6 raised to that is 6. So sigma means plus. Now, so I already made n 0, now we're going to make n 1. 5 to the first over 6 to the second, plus. So we made n 0, then 1, now n is 2. 5 to the second over 6 to the third, and so on. But you can tell that the series is geometric. I don't remember if I mentioned that here. This is geometric. So you can't find a common ratio unless it's geometric. So when we say geometric, we just mean there's a common ratio, which means any term divided by the one before it is always, in this case, 5 over 6. Because I got this by saying to myself, what do you multiply to 1 to get 5? What do you multiply to 6 to get 6 squared? And it works going from here to here also. 5 times 5 is 25, and 6 squared times 6 is 6 to the third. That is the common ratio. Since the absolute value of r is less than 1, the series converges. 2 a over 1 minus r. And by a, we mean whatever the first term is. Right here, this is a. Over 1 minus, this is r. A over 1 minus r. We multiply the numerator by 6. That's okay as long as I multiply the denominator by 6. So here's a summary. First of all, the word converges is part of the answer. It says tell whether the series converges or diverges. And it also says if it converges, find its sum. So summary, sigma 5 to the n over 6 to the n plus 1. N starts at 0 and goes forever. The sum of all these numbers, this infinite series, is 1. Now just remember, you're going to say the series diverges. If the series is geometric and the absolute value of r is 1 or more, then you're going to just say that the series diverges, meaning you cannot find its sum. It's impossible to find the sum. That's what we say when the absolute value of r is 1 or more. Okay, I just want to make one comment that is going to be important later on, and that is the following sentence. Where I write the sentence, I'm going to say the end. So, if the infinite series sigma a sub k, k starting at 1 and going to infinity, meaning a sub 1 plus a sub 2 plus a sub 3 plus a sub n plus, there's two places where there's 3 dots. If an infinite series converges, if the series converges, it doesn't matter if it's geometric, it's not important here, then the following will be true. The limit, and make that a little neater, the limit of a sub k, as k approaches infinity, will equal 0. I just want to point out that that's true for any time you have a series that converges. Like right here, here's a series that converges. And I say the limit of a sub k as k approaches infinity equals 0. What I mean is this term is close to 0. This term is even closer to 0. This is even closer to 0. That'll be true for any series that converges. So So let me look at another one to show you. Again, here's another series that converges. And so I'm observing that 3 is close to 0. That's even closer to 0. And that's even closer to 0. And even closer. These terms are getting closer and closer and closer to 0. That doesn't mean the sum is 0. Even if it was 30 over 11. This is just a characteristic to note about a series that converges. Now, this was one that converged. If we said that somewhere, converges. So you're going to notice that close to 0, closer to 0, even closer, closer, closer. The terms themselves are getting closer and closer to 0. And that's not true necessarily for a series that diverges. Like right here, this is a series that diverges, and you wouldn't say these terms are getting closer and closer to 0. That term is 2. Okay, this is closer to 0 than that, but this isn't. This is just as close to 0 as that is. Okay, the end for now.